Learn like a pro.
Hello and welcome. Today we are going to pull back the curtain on the magic behind pretty much all the electricity that we use. We are talking about the AC generator, that amazing machine that takes simple rotation and turns it into the alternating current that powers our entire world. Let's get right into it. So think about it for a second. How does something as simple as a spinning turbine, whether it's powered by wind or water or steam, how does that mechanical motion get transformed into the electrical energy that's flowing through the walls of your house right now? That's the big question we're going to tackle. You know, at its very core, the whole process is just a beautiful conversion of energy. We start with some kind of mechanical movement, gears turning, a coil spinning around. This kinetic energy gets passed through an external magnetic field, and thanks to something called the generator effect, it comes out the other side as electrical energy, in the form of that classic alternating current wave. To really get a handle on that generator effect, we've got to zoom way in. We need to look at the fundamental interaction that's happening on an almost invisible level. It really all comes down to how a simple wire plays with magnetic field. Okay, so this whole thing hinges on a core principle, Faraday's law. And what it says is, if you have a magnet and a coil of wire just sitting next to each other, well, absolutely nothing happens. The real key, the trigger for creating any electricity, is change. You have to move one relative to the other. You have to be cutting through those invisible magnetic field lines. That change is what gets a voltage going. And this right here illustrates the most crucial part of that whole idea. Just look at the vertical position on the left. You see how the wire is moving parallel to those magnetic field lines? It's not really cutting them at all, so the rate of change is zero, no electricity. But now look to the right, in that horizontal position. The wire is just slashing through those field lines at a perfect 90-degree angle. That creates the maximum rate of change, and you guessed it, the maximum voltage. Okay, so now we know that cutting these magnetic field lines creates a current. But which way does that current actually flow? Well, physics has given us this incredibly handy, pun intended, tool to figure that out. This is Fleming's right-hand rule. And it's basically a physical cheat sheet that perfectly connects the three key forces that are at play here. You've got the direction of the magnetic field, the motion of the wire itself, and the direction of the current that gets created because of it all. Go ahead and try it with me. Just take your right hand, point your first finger in the direction of the field, so that's from north to south. Now point your thumb in the direction of the wire's motion, and like magic, your second finger will then naturally point you in the direction of the induced current. As we're about to see, this simple rule is the entire reason the current alternates back and forth. So we've totally cracked the physics of how to induce a current. Awesome. But now we're staring down a serious engineering problem. How in the world do we get that electricity out of a coil that is spinning around and around nonstop? I mean, it's a really simple but absolutely critical question, right? If you just attached wires to it, they would immediately get twisted up into a tangled mess and snap. We have to find a way to maintain a solid connection while allowing for that endless rotation. And here is the really elegant solution engineers came up with. The ends of that spinning coil, they're connected to two continuous metal rings called slip rings. These rings spin right along with the coil. And then, pressing against them, you have these stationary carbon brushes, which are great conductors. They just sit there and whisk the electricity away to the external circuit. So the whole point here is that this setup is doing two jobs at once. Mechanically, it completely solves that twisting wire problem, and electrically, it creates this seamless, uninterrupted bridge for the current to flow from the moving world of the coil to the stationary world of our power grid. It's brilliant. All right, now that we've got all the pieces of the puzzle, we can finally connect the physical rotation of the coil directly to its electrical output, and what we get is one of the most famous and beautiful shapes in all of science. So let's follow the first half of this journey. At 0 degrees, the coil's vertical, so it's moving parallel to the field, right? The voltage is 0. As it rotates to 90 degrees, it goes horizontal, cutting those field lines at the maximum rate, and bam, we hit a peak positive voltage. Then, as it keeps going to 180 degrees, it's vertical again, and the voltage just drops right back down to 0. Now for the second half of the spin, remember Fleming's right-hand rule? That side of the coil that was moving up a second ago is now moving down, and what does that do? It reverses the direction of the current. So as the coil passes through 270 degrees, it hits a peak voltage all over again, but this time it's in the negative direction. Finally, at 360 degrees, it's right back where it started, vertical, 0 voltage, and ready to start the whole cycle over again. And here it is. This is where it all clicks into place. That smooth, alternating sine wave you see? That's not just some abstract graph. It is a direct, point-for-point blueprint of the coil's physical journey. Its zero voltage reading corresponds to its vertical movement. The peak voltage? That corresponds to that maximum perpendicular cut. It is a perfect marriage of mechanics and electricity. So we know how to generate an alternating current, but how do we control it? How do we make it stronger? It turns out there are three main levers we can pull to do just that. First off, we can just spin the coil faster. A higher speed means a greater rate of change, which gives us a higher voltage. Simple enough. Second, we can use a stronger magnet. This makes the magnetic field denser, so the coil is cutting way more lines with every single turn. And third, we can add more loops of wire to the coil. This basically multiplies the effect, since the voltage from each individual loop all adds together for a much bigger total output. Now here's a fantastic example of that in action. This generator is rotating at a frequency of 3 Hertz. That just means it's doing 3 full revolutions every single second. And if you look at the output, you can clearly see 3 complete sine wave cycles packed into that 1-second window. We can also see that the control levers, the speed, magnet strength, and coils, have been set to produce a maximum voltage of plus or minus 15 millivolts. So when you really think about it, it's not just about raw power. What a generator really does is create a consistent, predictable rhythm. The speed of the rotation, the strength of the magnet, and the number of turns in that coil, those are the instruments that set the very pulse of our entire electrical grid. So, we've seen how this incredible alternating current is born from something as simple as rotation. But that kind of brings up the next big question, doesn't it? How does this oscillating rhythm travel across huge distances and get transformed into the usable power that runs everything in our daily lives? Well, that is a fantastic story for another explainer.